I'll be talking about the electrical and magneto transport in nanocrystalline band ferromagnets. The organization of the talk is as follows. First, we'll identify different sources of electrical resistivity in metallic ferromagnets. Then I'll show you how one can unambiguously separate out different scattering contributions and also determine accurately their magnitudes. I will treat nanocrystalline nickel as an example to illustrate this approach. But this approach can very well be used for any metallic ferromagnet, whether it is crystalline, nanocrystalline, or amorphous. So quite general in scope. I'll talk about the magnetic resistance later on, and then I'll show you what the finite size effects bring in. Because most of you already know that the scattering of conduction electrons from impurities or imperfections or both give rise to what is called the residual resistivity. That is the value of resistivity as T approaches 0. It is limited by the scattering from imperfections or impurities. Then other contribution can be the charged scattering of electrons from one another, that is S electrons from D electrons, for example, and this is known as the Weber scattering, or later on known as the Fermi liquid behavior. Okay. So this contribution to resistivity goes as T square at very low temperatures. Then one can have also electron-phonon scattering, and there are two types of electron-phonon scattering. One is the phonon-induced non-spin flip intraband scattering, which is nothing but the Bloch-Brownian well-known expression, that is goes as T raised to power 5 at low temperatures. And then we also have phonon-induced non-spin flip interband scattering, SD scattering. This is Bloch-Wilson. Then we have this magnon-induced non-spin flip interband scattering, magnon-induced spin flip intraband, and interband scattering. It turns out that this contribution is actually 2 orders of magnitude larger than these two. So I will not go into this in this talk, but it can be demonstrated that is so. And this accounts for most of the contribution coming from magnons. And as you see in this expression, apart from this rho star, which is a measure of the electron-magnon coupling, which is basically the SD interaction, and this coupling constant also has the density of states at the Fermi level. This contribution also goes as T square, but it is corrected for the spin wave stiffness constant, which gets thermally renormalized in accordance with this relation. This contribution comes from the Stoner single particle excitations and when they interact with magnons. Then there is a renormalization of the spin wave stiffness, thermal renormalization of spin wave stiffness. The other contribution comes from magnon-magnon scattering. Okay. Now I'm just showing the zero field resistivity versus temperature data. This is raw data. And I want to show you through this type of approach how we can determine different scattering contributions unambiguously and also determine their magnitude accurately. As you can see, that what's happening is here I have given this is the average nanocrystallite size in nanometers, ranging from 10 nanometers to 40 nanometers. As you can see that, as expected, as as the crystallite size reduces, the residual resistivity goes up, whereas the temperature coefficient of resistivity near room temperature that increases with increasing particle size, increasing crystallite size. That is seen in this slide. So you see the residual resistivity falls as you go to higher crystallite size, whereas the temperature coefficient resistivity goes up. Now this can be understood clearly in the base of the fact that you have enhanced scattering of conduction electrons from atomic disorder or imperfections which are prevalent at the interfaces or surfaces and grain boundaries as D reduces, because as D reduces, the surface area increases, and hence the whatever disorder is there on the surface, that contributes to the residual resistivity. So residual resistivity is higher in the case of nanocrystallites which are around 10 nanometers. Now we have also measured this residual resistivity as a function of field. So one might wonder what this residual resistivity, I said there is coming from basically for imperfections and impurities. But it so happens that at absolute zero, if you have a multi-domain sample, then domain walls can give rise to scattering, spin scattering, because in the domain walls the orientation, spin orientation is changing continuously. So you could in principle have some contribution to the residual resistivity coming from the domain wall scattering, and also the fact that you have surface. Now at the surface then you can have spin disorder at the surface that could also give an additional contribution to the residual resistivity in principle. What we show through this experiment is that with field there is no change, practically no change in the residual resistivity, meaning thereby that these two contributions, which are spin dependent contributions, do not contribute much, okay, and hence they are nearly field independent. Why that is so is that because the range that we have chosen between 10 nanometers and 40 nanometers is almost close to the critical domain size. Hence there are no domain walls as such. So there won't be any domain wall contribution. That is understood. So that part can be understood. Now if you just go back a few slides, in this expression, if we have to determine this is the electromagnetic scattering contribution, we have to know the spin wave stiffness and its temperature dependence, and that can be obtained from magnetization data as a function of temperature. So to get this, because here we need spontaneous magnetization, so we need to extrapolate to zero field to get the spontaneous magnetization. That's why this normally what you do is you plot this M versus H isotherms in the form of arret plots, and then extrapolate the high field linear portion to H equal to 0, and the intercepts on the ordinate axis gives you the spontaneous magnetization as a function of temperature. So that's how we have determined the spontaneous magnetization, and then this spontaneous magnetization now as a function of temperature fit with the well-known spin wave expression, which is this, where this beta is a measure of the RMS exchange correlation length, that is the range over which the exchange interaction operates in these systems. And here again we have the same, here again this thermal renormalization is there. So here we can find out which of these gives dominant contribution. It turns out in this case it is the magnon-magnon interaction that renormalizes the spin wave stiffness. So this, so in this, by fitting this, we get spin wave stiffness constant at absolute zero, and also the thermal renormalization of spin wave stiffness caused mainly by magnon-magnon scattering. And you see now these are the fit parameters as a function of thickness. You see that the spontaneous magnetization at absolute zero and spin wave stiffness at absolute zero, they scale with the average crystallite size according to these power laws. So that would tell you that this average crystallite size is a relevant scale for spontaneous magnetization in these systems. These are just the fits to the intrinsic resistivity. That means, once you determine the residual resistivity, you subtract out the residual resistivity from the measured resistivity. So what you are left with is the intrinsic resistivity. Now we divide this into two temperature ranges where different scattering mechanisms are dominant, because it so happens that different scattering mechanisms dominate over different temperature regions. So if you try to fit the entire curve in the whole range with the one single expression, then you will not be able to get these contributions right. So that's why first you try to see what's happening below around 15 Kelvin. There is a story behind it which I'll tell you later on. Why 15, why not 10 or 20? That I'll come to. So what we have done is here we have tried to use the Bloch-Grunewaldsian formula for electron phonon contribution, scattering contribution, and electron magnon contribution is taken as T square. If you recall, just go a few slides back. If you take this, electron magnon contribution can also go as T square, provided there is no thermal renormalization of the spin wave stiffness. That means you have spin wave stiffness which is constant, doesn't depend on temperature. Then it can also go as T square. So not only you have the electron-electron scattering which goes as T square, you also have electron-magnon, coherent electron-magnon scattering, which also gives rise to a T square term. So then the question comes, how do you separate them out? How do I say whether this is actually the electron-electron scattering or electron-magnon scattering? So that's what we're trying to see here. Now here, as I said, that we are trying to fit the residual resistivity. We remove the residual resistivity from the measured resistivity and then try to fit it with different expressions. And what we find is that if you take the Bloch-Grunewaldsian formula, which is actually non-spin flip intraband scattering, that you are able to fit this intrinsic resistivity up to about 15 Kelvin by just using the Bloch-Grunewaldsian formula for electron phonon, and either you can have electron-magnon or electron-electron scattering. Both go as T square. So you are able to fit that, but what you see is that up to about 10 Kelvin or so, the intrinsic resistivity is completely accounted for by either the electron-magnon scattering or electron-electron scattering. That means T square variation is the one that accounts for the total resistivity, the total intrinsic resistivity up to about 10. The phonons part picks up only beyond 10, but it is still an order of magnitude smaller than what the contribution from electron-electron and electron-magnon scattering. Now, as I said, we have to find a way of distinguishing between these two, and that is provided by the sensitivity of these electron-electron and electron-magnon scattering to external magnetic field. So if you take the electron-electron scattering, since it is charge scattering, it does not depend on the magnetic field. Whereas you have electromagnon scattering, because when you apply the field, magnetic field, it creates a gap in the spin wave spectrum. And because of that, it makes the excitation, spin wave excitations difficult, in the sense that you have to pay a more higher energy cost to excite spin waves. So you have less magnons when you are at high fields to scatter electrons. Okay? So that means the electromagnon scattering will get suppressed quickly when you apply the field, magnetic field. Whereas electron-electron scattering would not get affected at all by magnetic field. So what you see here is that basically that the coefficient of t-square term is nothing but the slope of these curves, and you find that that slope does not change with field. So it's a clear indication that up to about 10 Kelvin or so, it is just the electron-electron scattering that is dominant. In fact, in literature, for more than 6 decades, most of the people believed that this t-square dependence comes from electromagnon scattering, not from electron-electron scattering. But a simple experiment, I don't know why they didn't think of a simple experiment to distinguish between these two. And this was seen in not only just iron, cobalt, nickel. It was seen in a large number of numerous alloys throughout all metallic ferromagnets of all kinds. They saw this t-square dependence and attributed it to just electromagnon scattering. And we show that that is not true. One has to do this experiment to find out whether that is so or not. Now I will come back to this question, why we have chosen one region below 15K. That is for historical reasons, because most of the systems showed that t-square behavior below, dominant t-square behavior below 15K. That's why we thought that, okay, if you have to make a comparison, then you better stick to that. So that was for historical reasons we took up to 15. But what we see is actually, if you go technically, then electron-electron scattering accounts completely the residual and the intrinsic resistivity up to about 10 Kelvin. Above that, phonon scattering also starts picking up. Okay, that has to be taken into account to get the full picture. Okay. Now we go step by step and see how we can identify first which are the dominant scattering mechanisms, and then try to get their, quantify them in terms of their magnitude. What I am showing you is, on this axis is the percentage deviation, that is deviation of the experimental value from the theoretical fit. Okay, that's what I am showing here. This is rho experimental minus rho fit divided by rho experimental percentage into 100. So what you see is that first what we do is we just take just the residual resistivity plus the electron phonon term, and it has two forms, as I said earlier. One is this Bloch-Brunesian form and another Bloch-Wilson. One is the non-spin flip intraband scattering, other one is the non-spin flip interband scattering. So you want to see whether it is the interband scattering that is dominant or intraband scattering caused by phonons. So from this what you learn is immediately you see that the deviations are systematic. That means this functional form, either this or this, does not really describe the observed temperature dependence. This we are doing it from 1.8 Kelvin to 300 Kelvin. Okay, so but between the two, it looks like that as if the Bloch-Wilson form fits the data better, marginally better, but still with systematic deviations, telling that is not really the form. Now what you do is next you add this electromagnon term. Okay, which goes as, first we'll take it as T square. That means basically we neglect the thermal renormalization of the spin wave stiffness. We take it to be a constant. Okay? So then what I am showing you is the deviations when you have block Grunesian and block Wilson plus a T square term, and you see what happens is that the block Grunesian gives you a lower percentage deviation compared to the block Wilson. It's just the reverse. Okay? And now in some cases you do see that it is not systematic. That means what we are by taking this electromagnon, by introducing the electromagnon term of T square form, we are able to reduce these deviations and describe the data better and better. Okay? Now, next step is obviously to include the thermal renormalization of spin wave stiffness, which we have neglected in this case, and then see what happens to the deviations. Now you can see this. Now we stick to the block Grunesian because we saw in the earlier slide with just added T square term, block Grunesian was giving better fit than the block Wilson case. That means the intra-band scattering was much more prominent than the interband scattering. Okay? Now, once we bring in the renormalization of spin wave stiffness into it, then you see now, first not only the deviations are reduced by order of magnitude, but they are now statistically distributed around 0. That means now you have got the right functional form, which describes your observed data properly, and we can actually estimate accurately their contribution, different contributions. So what we see now is that with that last thing that I showed you, so we find that Debye temperature, or this is the electron-phonon coupling constant, and electron-magnon, as I said, electron-magnon coupling strength, that is the interaction, electron-magnon interaction strength, that all these go as some powers of the average crystallite size. So this tells you now clearly that the crystallite size here happens to be the relevant length as far as both magnetism as well as the transport is concerned. Okay? Now next what we do is go to the magnetoresistance. Okay? Sorry, first I will show you these fits so that you just see because you can appreciate the different contributions, how they behave with temperature, in what temperature range which one becomes more dominant, and you can see even that. For example, here take any of these. First you see with a low, when the crystallite size is low, then you find that the major contribution is coming from the electron-phonon scattering. Electron-magnon scattering is not doing much, is a factor of 2 or so difference between them. Okay? And this is picking up now. But when you increase the crystallite size, then you see that they are becoming comparable. Okay? So that gap is reducing between them. And what is happening more is that the phonon part is getting suppressed. Magnon part does not change very much. And you can check that thing, even with the crystalline nickel. That is a bulk case also I have put for comparison here. And there is a temperature at which these two contributions are same. That is this so-called T star. And below that, actually the phonon term is much less important than the magnon term. But then there is a crossover. That beyond that particular temperature, the phonon term picks up more than the magnon term. But that crossover temperature shifts to higher temperatures as you increase the size. For example, here it was about 30 Kelvin. For nickel, it's around 60. Nickel, I mean bulk nickel. 60. So it just gives you an idea of how different scattering mechanisms become important in different temperature ranges, and you can even know their actual magnitude. And one can even understand why that should be so, that are shown here. For example, when you look at the phonon coupling, electron-phonon coupling, it is inversely proportional to the density of states at the Fermi level. Whereas, when you look at the electron-magnon coupling, it goes directly as the density of states. So what's happening with when you are decreasing the size, the slight size, so surface area is increasing, and so is the disorder, surface disorder is increasing. Because of that, what's happening is that the density of states curve is getting more and more smeared out, so that the density of states at the Fermi level are getting suppressed. That sharp peaks in the density of states near the Fermi level are getting level off, getting smeared, so that the average density of states at the Fermi level is decreasing. That's why they have an inverse relationship, as you can see, where the phonon part is decreasing, this other part is increasing. Because I have plotted it as 1 by d, root d. Okay? So this is the bulk value, for example. Similarly, this is the bulk value. Okay? So one can understand that why you should be seeing this trend, why one should increase and other should decrease. But the very fact that, as I said, they are going as some powers of the average crystallite size would mean that that is really the controlling length scale. Now I go to the magnetoresistance. Here, as we know that other contributions which are electron-phonon, for example, you don't expect that to get reflected in magnetoresistance. It will be only the electron-magnon part. And out of that electron-magnon scattering, it is basically the so-called spin flip interband. That is this type of scattering. Spin flip interband SD scattering, which actually gives rise to the magnetoresistance. Now, this is what theory would give you. Okay? And you can relate it. There are various ways of doing it. One is that for magnetoresistance, either you can measure the isotherms, like magnetoresistance versus field at different temperatures, or magnetoresistance versus temperature at different fields, fixed fields. So what we did was we measured magnetoresistance as a function of temperature at different fields, because we were measuring resistivity in zero field and at different field values, right up to 9 Tesla. So we could get both of them, that is, you can reconstruct one from the other. And here, this is the expression that we get for the electron-magnon contribution, which is the interband scattering contribution. But they actually measured, what you measure is this. This is the total, you measure the change in the total resistivity in field, magnetic field, not separately electron-magnon contribution, how it changes with field. So you have to recast that, your earlier expression, you have to recast it into what you see in experiments. So that is what this, finally, this expression is, and this is nothing but the zero field resistivity. That is this one. This we had already done, that exercise was done earlier with zero field, the resistivity. Now we do the same thing for the in-field, and then from that we calculate the magnetoresistance and then see how this expression forms. Now I want to remind you one thing, is that what I showed you earlier with the zero field resistivity is that we have got all these terms. We got this term, we got this term, we had this term for the whole temperature range completely. So we had a correct description for the resistivity in zero field. Okay? Now in the magnetoresistance, only thing that is there is this. This we knew, because I already showed you that this is zero field. This is a zero field electromagnet, and this electron-magnon scattering term. This we had already got in the analysis of the zero field resistivity. So the only term which is the leading term in that expression, just go back for a minute. There are other terms in the expression apart from this. This is just the leading term. There are other terms too. So if you take the leading term, 30 minutes out? 5 plus 5. Okay. So basically now this small h is nothing but g mu beta h by k beta t. It's renormalize that. So you get both field variation with field as well as with temperature, keeping one of them constant. Okay, and just go back just to so that you understand what I'm trying to say. Is this h is nothing but this stands for g mu beta h by k beta t. So from this I can have the variation either with h for a constant t or vice versa, at constant h with temperature. So in this expression, the only variable is this, eta. Eta only provides for the surface spin disorder, okay, and how that changes with when you apply the field, external field, how that will change with field, and how these electromagnon scattering at the surface would take place. So there will be some extra contribution coming from the surface, which is not accounted for in theory. Theory was done for a homogeneous system where there was no disorder. Okay, so it is just to take into account the disorder. So now you see that when you look at this is now magnetic resistance at different fields as a function of temperature. Okay, so these fits through that are based on that equation, where there is only one variable, which is eta. Okay? So that you see describes this data quite well. There are no more pre-parameters. Okay, only one pre-parameter. This is versus field at different temperatures. Okay. So it turns out that this eta also has some power law dependence on D. So this clearly shows that as far as this whole story is concerned, basically it is the average crystallized size which is the only controlling length scale in this problem. Okay. So with that I stop. This I have already given you. So if there are questions, I would be more than happy to answer them.